Today's lesson continues our work on probability as we study compound events. To start our lesson today, I'm going to give you a warm-up problem where you have 3 different combination locks. As you try to answer these questions, I want you to think about your thinking. And if you are unable to answer all of the questions, please don't worry, because this is what the lesson is going to be about maybe what you already know about solving these problems, but also learning some new techniques. So we've got a combination lock, a lot like the locks that are on your lockers or that you might use on your bike lock. And there's going to be 3 choices. So for choice A, the lock has 3 wheels numbered from 0 to 9. And there's a couple questions here, including how many possible combinations are there. So go ahead and pause the video, do some calculations, do some thinking, and then when you think you have an answer, come back to the video. The next choice for a combination lock is a lock that's numbered from 0 to 39. This is a lot more like the lock that you have on your locker at school. Each combination uses 3 numbers in a right, left, right pattern. So the question for choice B is how many possible combinations are there for this lock? Again, pause the video, do some work, come back for choice C. For choice C, the lock has 4 wheels. Each one of them has a different possibilities as indicated in the little chart. So then the question is how many possible combinations are there? Again, pause the video, do some calculations, and come back. So now that you've had those warm-up problems to get you to start thinking about compound events, I'm going to go back to the learning target and some vocabulary. So our learning target for today is to determine the sample space and the total number of possible outcomes and find the probabilities of a compound event. So there's a couple words in there that we want to make sure that we know what they mean. The sample space is the set of all possible outcomes of one or more events. And a compound event is 2 or more events, the probability of which is a number between 0 and 1. And it's the ratio of the number of favorable outcomes to the number of possible outcomes. So that's the same as any probability, but there's 2 or more events happening in one problem. One of the first things that we want to be able to do is find a sample space. And one of the ways that we frequently will do that is by making a counting tree. So my guess is that you've seen these counting trees before. I'm going to review how to do it, and then for homework tonight you'll get a chance to practice on your own. But again, I think you have probably seen this. It's where I have multiple options. So in this case, I'm going to think about going and getting some ice cream. I've got a couple of different flavors of ice cream. I have a couple of different containers that I can put it in, and I have a couple of different toppings that I might choose from as well. So you can think about what kind of ice cream you would like, but then we're going to look at the sample space by making a counting tree. So again, a counting tree is a kind of typical basic strategy that we might use. And in that we look at our different options. So for example, if I know that I have vanilla ice cream, I know that from vanilla ice cream I could have either a cone or a cup. I could also choose chocolate ice cream. And if I chose chocolate ice cream, I could also have a cone or a cup. Then for each of these I get to choose toppings. I'm actually going to come up with some abbreviations for my toppings. So I'm going to use C, so I'm going to make a little bit of a key, S, and W. So I could have a vanilla ice cream in a cone with either chocolate, sprinkles, or walnuts. Or I could have them in a cup, chocolate, sprinkles, or walnuts. I could have chocolate ice cream in a cone with chocolate, sprinkles, or walnuts. Or I could have that in a cup as well. So you get the point that we start to see this repeating pattern, and it helps us to determine the possible outcomes. So what I have done here is this group of different possibilities is called my sample space. So then I might ask you, how many possible outcomes are there? So the outcomes, I scrunched myself a little bit here, but the outcomes are vanilla. I'm going to actually add on to my key, vanilla chocolate. Let's call the containers, how about O and U? I'm just looking at the second letter because I already have C in multiple places. So my outcome might be vanilla cone chocolate syrup, or I could have vanilla cone sprinkles, vanilla cone walnuts, vanilla cup chocolate, vanilla cup sprinkles, vanilla cup walnuts. You get the idea, right? And I'm not actually lining it up very well either. For some reason I started writing bigger. So I'm gonna pause the video and write the rest of these so you don't have to wait for me to write them. So now I've listed my possible outcomes. Honestly, I don't usually list my possible outcomes like this because I can find those off of my counting tree. But depending on what the question asks you, you want to be familiar with listing outcomes like this. So if a question asked you to make a counting tree to determine the number of possible outcomes, you could just include what I have here in blue. If the question asked you to list the possible outcomes, you would want to include what I have here in red. Either way, the primary purpose for making a counting tree is to determine the number of possible outcomes. So if I have listed them all here, we can clearly tell that there are 12 of them. So I have a total of 12 outcomes. Now again, there will be times where you are asked to list the outcomes. But if the question just is, how many are there, then we can use something called the fundamental counting principle to determine the number of outcomes. So for many of you at this point, this is intuitive. Some of you probably even were doing this on the initial warm-up problems, where you're looking at how many options do I have for, I'm going to move this up just a little bit, how many options do I have for the counting, for the ice cream? So there's 2 of those. And then how many options do I have for the containers? There's 2 of those. How many options do I have for the toppings? There's 3 of those. So if I multiply those together, I get 2 times 2 is 4 times 3 is 12 possible outcomes. And that understanding that you can take the number of possibilities times the number of possibilities times the number of possibilities to get the total number of outcomes, that's called the fundamental counting principle. So many times we don't need to list all of the different possible outcomes. We just want to know how many there are, and that is one way of doing it. So let's look at another example of using the fundamental counting principle to determine the number of outcomes. Say, for example, I want to find the total number of possible outcomes of rolling a number cube and flipping a coin. So I'm going to start with the cube, and basically I know that on my cube I have 6 possibilities. So numbers 1, 2, 3, 4, 5, 6. And then when I flip a coin, I have 2 possibilities. So for a very straightforward example, I could get 6 different options here, 2 different options here. So using the fundamental counting principle, I know that I might have 12 outcomes. So for another example of using the fundamental counting principle, let's say that I have a closet in these things on the top are pants, and then I have shirts, and then I have shoes. So the question is, how many different outfits could I make from the shirts, pants, and shoes in my closet? If the question were to list the possible outcomes, you would want to make a counting tree and show the possibilities like we did with the ice cream problem. But if the question is just asking you how many different outfits could you make, you can use the fundamental counting principle to determine. Go ahead and pause the video, see if you can come up with a total number of outfits, and then unpause. So if you were able to clearly see that there are 4 pairs of pants and 7 shirts and 3 pairs of shoes, you would determine that there were 84 different outfits. So now let's go back to the problems that we did in the warm-up, and some of you may have had an idea of how to do these using some idea of the fundamental counting principle, although my guess is you wouldn't have been able to name it that way. But now let's look at our options. So on choice A for this lock, the lock had 9 wheels numbered from 0 to 9. Excuse me, 3 wheels numbered from 0 to 9. So for the first wheel, there were 10 possibilities. For the second wheel, there were 10 possibilities. And the third wheel, there were also 10 possibilities. So in that combination, we have a total of 1,000 options. Notice that what I choose for the first wheel does not depend on what I choose for the second wheel or for the third wheel. So these are what are called independent events, and we'll talk a little bit more about dependent events later in the week, but right now these are all independent. I have 10 possibilities for the first one, 10 for the second, and 10 for the third. So I have 1,000 combinations for this first problem. On the next one, I've got 0 to 39, so that's going to be 40 options, and I use those numbers in combination right, left, right. So I've got 40 times 40 times 40. Again, it would be highly unlikely that I would use the same number 3 times, but I could. It'd be, how you have to go past one number and land on it again, so that's a possibility. So 4 times 4 is 16, times 4 is 64, and I have 1, 2, 3 tens, so 3 zeros, so that one gives me 64,000 combos. And then finally on choice 3, for wheel, I put the first wheel, the second wheel, the third wheel, and the fourth wheel. And for the first one, I have 10 number possibilities. The second one, I have 20 letter possibilities. The third one, I have 20 letter possibilities. And the fourth one, I have 10 number possibilities. So on that one, I have 40,000 combos. So you can see now how we can use what we just learned about the fundamental counting principle to find the total number of combinations. The last part of today's lesson is to apply what we now know about finding the number of possible outcomes to finding the probability of a compound event. So in this situation, we've got 3 nickels, and we want to find the probability of flipping 2 heads and 1 tails. So the first step is we're going to use a counting tree, or the fundamental counting principle, or a combination of the two of them to find the number of possible outcomes. So we have 3 nickels, so I'm going to have my first nickel, my second nickel, and my third nickel. On the first nickel, I can either flip a head or a tail. On the second nickel, independent of that, I could flip a head or a tail, regardless of what I did on the first nickel. And then on the third nickel, I could also do a head or a tail. This way I could do a head or a tail. You get the idea and see the pattern. So I have a total of 8 possible outcomes. So that's going to become the denominator of my probability. And then step 2 is I want to, again, use the fundamental counting principle or a counting tree to find the number of, this should be the number of favorable outcomes. So in this problem, it asked me about flipping 2 heads and 1 tail. So I'm going to highlight my possibilities here. So a head, 2 heads, and a tail is right there. 2 heads